everyone. Hope you are doing very well. So, today we are going to do the DNF block elements theory part 3. So, let's begin with our topic of today's lecture, that is NCERT chapter 4 DNF block elements theory part 3. Today we are going to cover the NCERT section 4.3.4 to 4.3.6. Let's see. This is disclaimer. So today's objective of the class, after attending this lecture, you will be able to understand the general characteristics of D block elements and the general horizontal and the group trends in them. The topics that we have to be covered today according to the NCERT are the first one, the section 4.3 general properties of transition elements D block, 4.3.4 oxidation states, following some example from 4.3 to 4.4, and in text question 4.3 to 4.4. Then our next subsection, trends in the M2 positive to M standard electrode potentials, and following the another subsection, trends in M3 positive to M2 positive standard electrode potential. Then we will conclude with the summary and key points to remember. So let's begin. Let's start with our first topic, that is general properties of transition elements, which covers in the D block. So some properties which we have done already and which we are going to do today are, so physical properties, variation of atomic and ionic sizes, ionization enthalpies. These topics we have done. Today we are going to cover oxidation states, trends in the M2 positive to M standard electrode potentials, trends in M3 positive to M2 positive standard electrode potentials, and in the later lectures we will going to cover these general properties. Okay, yeah, so these general properties we will going to cover in the later coming lecture. So let's start. The first topic which comes in a subsection 4.3.4, that is oxidation states. Now the variety of oxidation state which is shown or which we can show in the transition elements. So one of the most notable feature of transition elements is the great variety of oxidation state they exhibit in their compounds. So you can see this table where we have given the first series, that is 3D series in the transition elements, and covering from the scandium to zinc, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, and their respective oxidation states you can see. You can observe some important things here, that scandium and zinc is only showing one oxidation state, that is +3 and +2 respectively. Manganese is showing the maximum number of oxidation states, and the trend you can see like +2 in almost every elements except the copper and the scandium. Okay, so the location of maximum oxidation states, the elements that display greatest number of oxidation state in the transition element are typically found in or near the middle of the series. You can also see that in this given table, that in the middle of the series we have manganese, which is showing the maximum number of oxidation numbers or oxidation states, and near to that middle of the series chromium and iron existing, which is also showing their maximum number of oxidation states, right? So this is generally observed that the elements in the transition state, if you see in the series, in middle or in near of the middle of the series, typically the greatest number of oxidation state is found, which is shown by the elements. So for example, here manganese we just have seen, which is a prime example, which is showing all the oxidation state from +2 to +7. Okay, +7 maximum, minimum +2. Now, the reasons of fever oxidation state at extremes. Now, we have seen at the table where at the extreme points, the left hand side and the right hand side, the rightmost and the leftmost side, the oxidation state is very number is very less. Right? That means only scandium and zinc is only showing one oxidation state. What is the reason behind that? So early in the series, if you see scandium and titanium, fewer oxidation state is due to too few electrons to lose or share. Okay, so oxidation state is shown only like in one number by the scandium or in three by the titanium because they are having very less electrons to lose or to share with another element to show the particular oxidation state. Scandium plus 2 is virtually unknown, and also scandium plus 2 is virtually unknown. That means it is rare. Titanium plus 4 is more stable than titanium plus 3 and plus 2. So these are the three oxidation states shown by the titanium, in which the titanium in the plus 4 is considered as more stable than the titanium plus 3 and plus 2. Why is it so? It is directly depend upon its electronic configuration. You can see, so you can relate it to that. The titanium electronic configuration is argon 3d2 4s2. Okay, so in the outermost orbital 3d2 4s2, 4 number of electrons are coming from 2 from the s orbital, 2 from the d orbital. Titanium in plus 4 means it has loosened its 4 electrons from the outermost, so that means it is attaining its noble gas configuration, which is kind of stable, more stable. So that's why the titanium in the plus 4 is more stable than the titanium in plus 3 or the plus 2. Now later in the series, we have observed copper and the zinc, where very fewer oxidation state is shown by them because of too many d electrons they have. So this means that less orbitals are available to share the electrons with the other atoms for higher valency. And for this reason that they have too many d electrons, so the orbital which are going to be available for the sharing of electrons is lesser. That's why they are existing in lesser number of oxidation states. Zinc has only one oxidation state, that is plus 2. Importantly, no d electrons are involved in this oxidation state. Okay. Zinc in plus 2, that means if you see the configuration, 4d argon 4d10 3s2 4s2, sorry, 3d10 4s2. Okay, so argon 3d10 4s2. Now when it loses its 2 electrons, it becomes zinc 2 plus, right? And it has a configuration of argon 3d10, which is d10 means the fully filled stable configuration. So zinc has only one oxidation state, that is plus d, and no d number of electrons, d electrons, that means electron from the d orbital, are involving in this plus 2 oxidation state shown by the zinc element. Maximum oxidation states and their stability. The maximum oxidation states of reasonable stability generally corresponds to the sum of s and d electrons for the elements up to manganese. Okay, so maximum oxidation state, which is having a reasonable stability, generally contain the sum of s and d orbital electrons for the elements up to manganese if you talk about the 3D series. For example, titanium oxide dioxide. So Ti, it is here in this compound existing in plus 4 oxidation state, which is the maximum oxidation state shown by the titanium, and also it is stable compared to its another oxidation states, right? Why? Because in the titanium plus 4, it is losing its 4 electrons, 2 from the s orbital, 2 from the d orbital. So sum of s and d orbital electrons it has loosened, and then it has attained plus 4 oxidation state, which is going to be stable because in the plus 4 oxidation state it has a noble gas configuration, right? And another example is vanadium dioxide positive. So in the vanadium we have it as the plus 5 oxidation state of it, right? So vanadium in its plus 5 oxidation state is stable because according to its configuration argon 3d 3 4s2, 2 electrons from the s orbital, 3 electrons from the d orbital. It has loosened and it becomes stable in the +5 oxidation state because it is attaining noble gas configuration after losing 5 number of electrons. Similarly, chromium in +6, O4 2 negative. Chromium in +6, that means the same reason that it has loosened 1 electron from s orbital, 5 electron from the d orbital, and attain the noble gas configuration and become chromium +6, okay, which is going to be the stable or maximum stable oxidation state. Then is manganese O4 negative, which is where the manganese in the +7 is having like a maximum stable oxidation state, right? So manganese in the +7 is having like good oxidation state, like stable oxidation state, because it has loosened its 5 electrons from the d orbital and 2 electrons from the s orbital. Following manganese, there is a rather abrupt decrease in the stability of higher oxidation states. So elements in the higher oxidation state kind of uh, getting decrease in their stability, okay, like after manganese, manganese, the elements which are coming, which are having higher oxidation state, is having decrease in their stability. So this trend is after the manganese. Typical species observed after manganese are iron in +2 and +3, cobalt in +2 and +3, nickel in +2, copper in +1 and +2, and zinc in the +2. Okay. Now, origin of variable oxidation state in the transition elements. So, variability of oxidation state in transition elements is direct consequence of incomplete filling of their d orbitals. There are incomplete filling of the electrons in the d orbitals of transition elements, due to which they show variable oxidation states. Crucially, their oxidation states typically differ from each other by unity. So it is observed that in transition elements, the oxidation state typically differ from each other by unity, means 1. For example, vanadium having +2, +3, +4 and +5 oxidation state. So +3 and +2, that means only one by only one unit the oxidation state is differing from each other, right? This is a contrast to known transition elements. So if you see, this is basically by unity, if oxidation state is differing from each other, then this is the thing shown by the transition elements. But if you talk about the non-transition elements, where the oxidation state differ by unit of 2, like if something is, like if some element, a non-transition element is existing in +2, then it will exist in +4. Okay, so the oxidation state in them differ by a unit of 2. Trends in the oxidation state stability within the D block groups from group 4 to 10. Interesting feature is observed when you're looking at the variability of the oxidation state within the groups of D block elements, especially the groups 4 through 10. Okay, so an interesting feature is kind of observed when you're looking at the variability of oxidation state shown by the D block elements, especially from the group 4 to group 10. Opposite trend to P block. The interesting feature is that it is showing the opposite trend from the P block elements. So while the P block elements show preference for lower oxidation states in heavier members, the opposite is true in the D block groups. Okay, so what we are saying that in the D block groups, the heavier metals are kind of stable in their higher oxidation state. Okay, and if you observe in the P block elements, the heavier metals or the heavier members in the P block are stable or kind of show the preference for lower oxidation state. That means heavier members existing in lower oxidation state due to the inert pair effect. But it is opposite in the D block, that heavier members exist in or stable or prefer the higher oxidation state. For example, if you take the group 6, molybdenum in the +6 and tungsten in the +6 found to be more stable than the chromium in +6. Okay, so if you see group wise, the molybdenum and the tungsten in the plus 6, that means the heavier, if you we are seeing the down the group. Okay, so molybdenum and tungsten, which are heavier members in the plus 6 in the higher oxidation state, are more stable than the chromium in the plus 6. Okay, consequently, chromium plus 6, for example, as a dichromate in the acidic medium, is a strong oxidizing agent. That means it is kind of oxidize others and get reduce itself. That means it will go from plus 6 to plus 4 and plus 5 and plus 3. Okay, whereas molybdenum trioxide and tungsten trioxide are not. Okay, they are not like chromium in its dichromate in oxide form in plus 6 oxidation state act as a strong oxidizing agent. That means it get reduce itself and oxidize others. Whereas if you talk about the molybdenum oxide and the tungsten oxide, they are not acting, or they are not considered as a strong oxidizing agent because they are stable in plus 6 oxidation state, right? Low oxidation state in the complex compound. Low oxidation states are observed when a complex compound contains ligands that possess pi acceptor character in addition to their sigma bonding capabilities. Okay, so when a complex compound contains ligands that is possessing pi acceptor character in addition to their sigma bonding capabilities, then the metal is showing a low oxidation state. Okay, so some ligands are there. Okay, ligands join or form the bond by the central atom or by the transition metal in the complex compound by sigma bonding, but some ligands possess the pi acceptor character due to which the metal will going to show the lower oxidation state. For example, in the compounds like nickel tetracarbonyl and iron pentacarbonyl, the oxidation state of both nickel and iron here is 0. Okay, why? Because here the carbonyl, that is CO, is a strong pi acceptor ligand. So it act as a, or it possesses the pi acceptor character, the carbonyl ligand. Okay, we will see this effect also in our upcoming lecture coordination compound, where we will study about the synergic effect shown by the carbonyl ligand, where what happens, the sigma bond formed between the metal and the carbonyl ligand by the donation of lone pair of electrons which are present on the carbonyl carbon to the vacant orbital of the metal. Meanwhile, the pi bond will form by the donation of electron from filled d orbital of metal to the vacant anti-bonding, that is pi star orbital of carbon monoxide, that is carbon. Okay, so due to that, the pi acceptor ligand we are calling the carbonyl as. Okay, and due to this the synergic effect will come, and due to this the metal in this complex will going to show or will going to exist in the lower oxidation states. Okay, let's do an example. Example 4.3, which is covering the NCRT section 4.3.4. The example is that name a transition element which does not exhibit variable oxidation state. So you have to name the transition element which is not going to exist in variable oxidation state, different oxidation state. Okay, so you have some time, try to solve this, and then we will see the correct answer. Okay, let's see. So for this example, let's understand the transition elements first of all. So the transition elements are found in the D block of the periodic table. They typically exhibit multiple oxidation state due to involvement of d electrons in the bonding. Identifying scandium. Now, scandium is first element in the D block with atomic number of 21. So if you look at the electronic configuration, it will be argon 3d1 4s2. So 2 electrons in the outermost orbital in the s orbital and 1 electron in the d orbital. Oxidation state of scandium. So scandium form ion when it loses its 3d and 4s electrons, right? Because it's not big deal. 4s, it can lose the 2 electron from 4s and 1 electron from d and attain a noble gas configuration, right? So it have to lose its 3d and the 4s electrons to become an ion. So most common oxidation state for scandium is +3, which occurs when it loses all 3 valence electron present in its outermost orbital, which is outermost shell, which is 2 from the 4s and 1 electron from the 3d orbital. Stability of +3 state. So after losing these electrons, scandium achieves the electronic configuration of argon, which is a noble gas, okay, which is stable noble gas configuration. Everyone wants to be a noble, wants to attain a noble gas configuration to achieve the stability. Okay, so this stability is a key reason that after donating its 3 electrons, it becomes +3 and it becomes stable because it kind of stabilized by its electronic configuration of argon. So this stability is a main reason that why scandium does not exhibit variable oxidation states like other than +3. The conclusion that since the scandium primarily exists in +3 oxidation state and does not show other oxidation states, it is the transition element that does not exhibit variable oxidation state. So this is going to be our answer, that is scandium. Let's solve an in-text question 4.3 covering the NCERT section 4.3.4. Which of the 3D series of transition metals exhibits the largest number of oxidation states and why? You have to tell that in the 3D series of transition element, which is going to exhibit the largest number of oxidation states and why. So you have given some time. Try to solve this, analyze this, and then we will see the correct answer. Okay, let's see. So for this question, the manganese, whose atomic number is 25, shows maximum number of oxidation state. Why? Because of its electronic configuration, which is 3d5 4s2, the outermost electronic configuration. Okay, so manganese in the 3D series existing, having atomic number 25 and also showing the maximum number of oxidation states. Why? Because of its electronic configuration showing 3d5 4s2, where 5 number of unpaired electron is present, so and also 2 from the s orbital. So as the 3d and 4s are close in the energy, it has maximum number of electrons to lose or share. Why? Because all the 3d electrons are unpaired. Okay, hence it will going to show the maximum oxidation states from +2 to +7 after losing the electrons one by one. Okay, it is going to show +2 +3 +4 +5 +6 and +7 oxidation states, which are in the 3D series maximum number of oxidation states shown by some element, which is manganese. Okay, so let's move to our next subsection, that is 4.3.5, which is trends in the M2 positive to M standard electrode potential. Thermochemical parameters and electrode potential E0. Thermochemical parameters, like those in a given table, describe the energy changes when the solid metal atoms transform into the M2 positive ions in the solution. So we are here talking about the electrode potential, where the metal is converting to the M2 positive. So M is representing the metal which is converting from M to M2 positive ions in the solution. Okay. So you can see this given table where some parameters is going to describe the energy changes when the metal is converting to M2 positive ions. You can see we have given the metals titanium, vanadium, chromium. So these are 3D series metals. Okay. It is here in this, like in this column, we have given the atomization enthalpy of atomization, the energy going which you are going to need for converting the metals into the free atoms. Here the ionization 1 enthalpy, here the ionization 2 enthalpy, and here in this column we have hydration enthalpy for the ion, and here we have E naught value, that is electrode potential. Okay, so the energy changes when the metal is converting to M2 positive. So a lot of steps is involving when the metal is converting to metal 2 positive. First of all, the metal is going to present in the solid state, right? So first of all, it needs to convert into the gaseous states, in which we need the this energy, that is atomization energy. Okay, then metal in the gaseous states going to convert in the metal in the +1 in the gaseous states, right? So in which we are going to need the ionization enthalpy 1. Then metal in the +1 will going to convert to metal in the +2, in which we are going to need the ionization enthalpy 2. And from that metal in the +2 in gaseous state, going to convert in the metal in +2 in aqueous state, is going to need the hydration enthalpy. Okay, so this is how different energy changes are involving when you're talking about the M to M2 positive conversion into the ion, like metal conversion transformation into the metal 2 positive ions. Okay, so we have given like different data for different energy changes. Okay, so the E naught value for copper is positive. That means the copper is possible to oxidize, right? And then other elements are having the decreasing trend of negative values of the E naught. These parameters are directly related to the standard electrode potential of the metal. So the parameters of the atomization energy, the ionization enthalpy 1, ionization enthalpy 2, hydration enthalpy, and the E naught value, they are directly related to the standard electrode potential of the metals. Okay, why? Because as I said that the metal going to convert to M2 positive by the three steps, that firstly it will convert to the solid to the gaseous, then from metal to metal plus, then metal plus to metal 2 plus, and from metal 2 plus gaseous to metal 2 plus X. Okay, so 3 to 4 steps it will going to need, and it is going to relate to the E naught. Like direct conversion from metal solid to metal 2 positive aqueous is in which the E naught is going to be the energy that is going to decide the conversion, but it is involving various steps, which is the in which we are going to need the atomization enthalpy, the ionization enthalpy 1, ionization enthalpy 2, and hydration enthalpy. So they both are related to the E naught value. Okay, so basically E naught is this ionization enthalpy 1, ionization enthalpy 2 plus hydration enthalpy and atomization enthalpy. Okay. Now thermochemical parameters and electrode potential. So the observed E naught values are often compared with those which are calculated from the thermochemical data. So we have two E naught values. First one is of the observed one, and second one is the calculated one. So we observe and we calculated the E naught value, and then we compared from the data as shown in the given figure, which is this one, the given figure, where the graph is given between the standard electrode potential in the volt and the D block elements from the titanium using the 3D series. If you see, there is an increasing graph. It is decreasing at the manganese, and also you can see that only copper is existing in the positive value of the standard electrode potential, and all the other elements are having the negative electrode potential. Okay, only copper is having the positive electrode potential. That means it is possible to oxidize. Okay, if you see another elements, the manganese is having a sudden lesser standard electrode potential, you can directly relate it with its electronic configuration, which is 3d5 4s2. Okay, so 3d5 4s2 means when it releases two electrons, that means the ionization energy 1 and the ionization enthalpy 2. Okay, that is going to be the lesser, right? And then the another energies will be hydration enthalpy and the atomization energy. So because the ionization enthalpy 1 and ionization enthalpy 2 is going to be lesser, the electrode potential value is going to be lesser for the manganese. Similarly, uh, if you observe, we have the cobalt and the zinc. Calculated values are lesser, and also nickel lesser than the observed values. Nickel and the zinc, you can observe that the calculated value is more negative in for the standard electrode potential than the observed value. Why is it so? Because basically, if you look at the hydration enthalpy for these elements, the hydration enthalpy is more negative for these elements, which is why there is unexpected decrease in the standard electrode potential value in the nickel and also the zinc. Okay, so the hydration enthalpy is more negative, and we said that E naught will going to be the sum of these ionization enthalpies and the hydration enthalpy and atomization enthalpy. And if the ionization enthalpy is more, the hydration enthalpy is going to be more negative for these elements, then the standard electrode potential will show the unexpected decrease in the E naught value of this nickel and the zinc. Okay, so this is figure 4.4, in which we have seen the observed and the calculated values for standard electrode potential, that is M2 positive to M0 of the elements titanium to the zinc. Now, unique behavior of copper. So copper exhibits unique behavior by having a positive E naught value. So as I said, the copper is existing in the positive E naught value area in the graph we just have seen. So copper exhibit a unique behavior having positive E naught value, which is a key characteristics that set it apart. So due to the positive E naught value of it, copper is unable to liberate the hydrogen gas from the acids. Only the oxidizing acids like nitric acid and hot concentrated sulfuric acid will react with the copper, and in these reactions acid themselves are reduced, not the copper being oxidized to produce the hydrogen. Okay, so copper is not going to be oxidized, okay, and only it reacts with the oxidizing acids like nitric acid and hot concentrated sulfuric acid, in which only acid are going to be reduced themselves. Okay, so the reason for copper's positive E naught is that the high energy which is required to transform the solid copper into the copper 2 positive ions in the aqueous solution is not sufficiently balanced by its hydration enthalpy. Okay, so copper from solid copper to the copper 2 positive aqueous ions, the high energy E naught that is going to be required for this conversion in the aqueous solution is not going to be balanced by its hydration enthalpy, because its hydration enthalpy from the copper 2 positive gaseous to copper 2 positive aqueous is very very less, okay, comparative to the atomization energy and the ionization energy sums, ionization enthalpy sums for the copper. Okay, so that's why we are saying that E naught required to transform the solid copper to positive ion is not sufficiently balanced by its hydration enthalpy, due to which the copper to positive is not possible. General trends in the E naught values across the series. There is general trend towards the less negative E naught values if you move across the transition series, right? So in the E naught value, we have observed that the trend we have observed is that E naught value is moving towards less negative when you move across the transition series. This trend is linked to general increase in sum of first and second ionization enthalpies across the series. So why is it so that the E naught value is like E naught values is become lesser and lesser negative when you move across transition elements? Because there is generally the increase in sum of first and the second ionization enthalpies across the series if you move, due to which the E naught value will decrease. higher ionization energies make it harder to form the M2 positive ion. Okay, if the ionization energy is increasing, that means formation of M2 positive ions is harder or difficult, leading to less negative or even positive E naught values. Okay, that's why the positive E naught values is becoming across the series. That means we are leading to less negative values of the E naught. Exceptions to the trend and their explanations. So it's important to note that E naught for manganese, nickel, and zinc are more negative than might be expected based on the general trend. As I have mentioned, that in the graph, the E naught values for manganese, nickel, and zinc, they are showing the more negative than might be expected from the general trend. Okay, manganese was showing the sudden decrease, and the nickel and zinc was showing the sudden decrease in their calculated value than the observed value. So these are important exceptions which we have to remember. So manganese, the more negative E naught value for manganese, because it is related to the stability of half-filled D subshell of manganese 2 positive, that is D5 configuration. Okay, so manganese is having in the 2 positive D5 configuration, which is why the E naught value of manganese is more negative. That means it wants to convert to manganese 2 positive to attain the half stable or half filled D subshell to become the stable one, right? Similarly, for the zinc, the more negative E naught value for zinc is linked to the stability of completely filled D10 configuration in zinc 2 positive. Okay, why zinc is showing the like more negative value? Because uh, you can link this with the stability of completely filled D10 configuration of zinc 2 positive, because zinc wants to convert to the D10 configuration, which is going in which the zinc is going to attain the stable fulfilled D10 configuration, and that's why it is showing the more negative E naught value. That means it wants to convert from zinc to zinc 2 positive to attain the completely filled D10 configuration and become stable. Similarly, for the nickel, the E naught value for nickel is specifically related to its high negative hydration enthalpy, that is delta hydration enthalpy among the series. Okay, so E naught value for the nickel is specifically related to the highest negative hydration enthalpy the nickel is having. Okay, so nickel have highest negative hydration enthalpy among the series, due to which the hydration enthalpy kind of like decrease the E naught value also, but because if the hydration enthalpy is highest negative for the nickel, the E naught value is going to affect, and E naught value will going to decrease for the nickel. The very favorable hydration enthalpy makes the formation of aqueous nickel 2 positive more energetically beneficial, contributing to a more negative E naught value. Okay, so favorable hydration enthalpy makes the formation of aqueous Ni2 plus more energetically beneficial, contributing to more negative E naught. Okay, so this hydration enthalpy is favoring the formation of nickel 2 positive ion as a more energetic one, because it will going to like increase or show the E naught value more negative for the nickel. Okay, let's do an example 4.4 from the NCRT section 4.3.5. The example is that why is the chromium in the 2 plus reducing and manganese in the 3 plus oxidizing when both have D4 configuration? So you have given some time, try to analyze this, and then we will see the answer. Okay, let's see. So for this question, the chromium 2 positive is reducing because its configuration is changing from D4 to D3. and the latter have a half filled T2G level. Okay, so if you talk about the chromium 2 positive, it is reducing. It will act as reducing one because its configuration will change from the D4 to D3. Okay, and also it will going to attain the half filled T2G level. So basically, in the D block electrons, the splitting happens between the two energy levels. One is Eg and the another one is T2G, which are separated, and these two energy level are also separated by some energy difference. Okay, now T2G level have their three spaces, Eg level has two spaces. Okay, so that because D orbital have five spaces in which each space can occupy two number of electrons, that means maximum 10 electrons can be filled in the d orbital, right? Similarly, when you split the d orbital electrons, it will attain Eg or T2G level, where T2G having three spaces and Eg have two spaces to fill the electrons. So D4, when you divide it, or D4 to D3 when it convert the configuration, so the T2G level is going to filled by one electron each. The each space is filled by one electron each. That means you will get half filled T2G level, which is going to be stable one. And the change from Mn3 positive to Mn2 positive, that means it is going to result in the half filled, that is D5 configuration, which has extra stability, right? So that's why we are saying that chromium 2 positive is reducing. That means it is going to reduce others and get oxidized itself. And also the manganese 3 positive to manganese 2 positive is oxidizing. Manganese 3 positive is oxidizing because it is going to oxidize easily others and get reduced itself, become Mn2 positive to attain the half filled D5 configuration, which is which is attaining of extra stability, right? So D5 configuration, which going to give the manganese extra stability, and that is why we are saying that chromium 2 positive is going to be reducing and manganese 3 positive is going to be oxidizing. Okay, so the stability of half filled D subshell in the manganese 2 positive and completely filled D10 configuration in zinc 2 positive relate to their E0 values, whereas the E0 for nickel is relating to the highest negative value of hydration enthalpy. Okay, so chromium, that's why here is going to be reducing, and manganese, that's why here is going to be oxidizing. Okay, and then now let's try an exam, an text question 4.4 covering the NCRT section 4.3.5. The question is that E naught from M2 positive to M value for copper is positive, that is positive 0.34 volt. Now, what is the possible reason for this that you have to tell? Hint we have also given that consider its high atomization energy and the low hydration enthalpy. Okay, so you have to tell that what is the possible reason behind the E naught value for copper as positive. So you have given some time, try to solve this, then we will see the correct answer. Okay, let's see for this question. For a metal, E naught value is related to sum of enthalpy changes, right? In the following terms, like metal from the solid is going to attain the atomization energy to convert to the gaseous state of the metal. Okay, so atomization energy, that is atomic enthalpy, which is going to be positive here. Now, this gaseous metal is going to use the ionization enthalpy to convert to the metal 2 positive ions in the gaseous form. Okay, So this delta IH is ionization enthalpy, which is positive. Again, the metal in the 2 positive in the gaseous will going to like use this hydration enthalpy, which is negative here, to convert to the M2 positive in the aqueous form, right? So these are the like energies whose sum, like these sum the sum of these enthalpy changes is going to be related to the E naught of M2 positive to M. So copper has a high atomic enthalpy and low hydration enthalpy. Okay, high atomic enthalpy, that means this much, this one, and the low hydration enthalpy, that means this one, the conversion of M2 positive gaseous to M2 positive aqueous. Hence, the value of the E naught for the copper is positive. Okay, it has high atomic enthalpy and lower hydration enthalpy, and that means the ionization enthalpy will going to be positive, right? And negative value is lower, like it has less negative value, and higher this atomic enthalpy. So this is also higher, this is also positive. So E naught value of the copper to positive to copper is going to be positive. Hence, high energy of transformation of copper in the solid into copper 2 positive in the aqueous is not balanced by its hydration enthalpy, because it is lower for the like copper solid into the copper 2 positive aqueous conversion. Okay. Now, understanding the E naught of M3 positive to M2 positive values. The E naught for this M3 positive to M2 positive values indicate the relative ease of reduction of an M3 positive ion to an M2 positive ion. So you can see in this table where element is given from scandium to zinc from 3D series, their atomic number, electronic configuration in each ionic or in each oxidation states, their standard electrode potential in M2 positive to M and M3 positive to M2 positive. Okay. So lower, that is more negative value of the E naught, means the M3 positive is harder to reduce. Okay. Or M2 positive is more stable. Okay. So more negative value of the E naught means that M3 positive is harder to reduce, harder to convert to M2 positive ion. Or higher, that is more positive value, means that M3 positive is easier to reduce. That means M2 positive is less stable compared to M3 positive. So M3 positive is easier to reduce to like M2 positive. That's what the higher value of the E naught is telling you. Specific trends and the explanation for the E naught of M3 positive to M2 positive value. The first one is scandium. So scandium, the low value for scandium of the E naught from M3 positive to M2 positive reflect the exceptional stability of scandium 3 positive ion. So scandium 3 positive ion achieves a noble gas configuration in which fully empty d subshell like argon is present, which is highly stable. Next is zinc. Zinc element have highest value of E naught from M3 positive to M2 positive. This is because it requires significant energy to remove an electron from highly stable D10 configuration of zinc 2 positive to form the zinc 3 positive, right? So it has highest value of the E naught value because zinc is already having 310 4s2. So it will going to require a significant amount of energy to remove the electron from highly stable D10 configuration of zinc 2 positive to form the zinc 3 positive, which is generally not observed because D10 is stable. Why it want to like donate its one electron to become the unstable? This makes the zinc 3 positive very difficult to form, and thus the zinc 2 positive is extremely stable here. That's why we are having the E naught value of it as highest. Next exception or next trend we have is for manganese. The comparatively high value for the manganese indicates that manganese 2 positive is particularly stable because it is having the configuration 3d5 4s2. So 2 positive after 2 positive it will going to attain 3d5. So high value for manganese indicates that Mn2 positive is particularly stable. So Mn2 positive has a high filled D5 subshell which confers the spatial stability due to the exchange energy. Okay, so Mn2 positive has D5 subshell which is half filled and which is going to get the spatial stability due to the exchange energy. So this makes it harder to oxidize the manganese 2 positive to manganese 3 positive because manganese 2 positive is already stable. Thus, manganese 3 positive is readily reduced. The next one is iron. Comparatively low value for iron signifies extra stability of iron 3 positive. So iron in the 3 positive is having extra stability. Why? Because iron 3 positive also possesses half filled, that is D5 configuration. Because iron is having 3d6 4s2. After releasing 3 electrons, it will attain D5 configuration, which is half filled and stable, which make it more stable than Fe2 positive. Fe2 positive is D6, Fe3 positive is D5. So this makes Fe3 positive relatively harder to reduce to Fe2 positive because Fe3 positive is already stable. Now vanadium, the comparatively low value for vanadium is linked to the stability of the vanadium in the 2 positive state. Okay. So vanadium 2 positive has a D3 configuration in an octahedral crystal field. These 3 electrons occupy half-filled T2G level. We have explained it, which provides extra stabilities because T2G have only 3 spaces available to fill the electrons, and these 3 electrons will going to attain those 3 spaces, and we got half-filled T2G level, which going to provide the V2 positive extra stability. This makes V3 positive harder to reduce to become V2 positive. Okay, let's cover the summary for today's lecture. So today we have covered the NCRT section 4.3.4 to 4.3.6. Firstly, we have seen the oxidation states, variety shown by the transition elements due to incomplete d orbitals, and maximum oxidation states was found in the middle of the series. Fever at extremes, we have also observed that in the early, due to the few electrons, and in the late, due to the too many d electrons, we have fever oxidation state shown by the elements. Higher states are more stable for heavier d block elements. For example, we have seen that molybdenum and the tungsten, the plus 6 is more stable than the chromium if you look at the along the group. So heavier metal are more stable in the higher oxidation state. Zero or low oxidation state with pi acceptor ligand we have observed where the ligand, for example, are pi acceptor like in carbonyl CO. Next, we talk about the electrode potential value. So it is related to the metal in the solid conversion to metal in the 2 positive aqueous energy. The E naught value is related to this conversion. So copper has a positive E naught. That means it is not going to liberate the hydrogen when it's going to react with the acid. Why? Due to its poor hydration enthalpy balance. General trend was that across the series, the E naught value is less negative. Exceptions was manganese because it is attaining D5 configuration. So it wants to attain the D5 configuration. That means it will show more negative. And zinc is also going to attain the D10. So it wants to attain the D10 for extra stability. That's why their E naught values were more negative. And nickel, the E naught value of nickel was more negative due to its high hydration enthalpy. Now M3 positive to M2 positive potentials indicates the ease of M3 positive reduction to the M2 positive. Scandium having low value because it is highly stable in the 3 positive because it is having noble gas configuration after releasing its 3 electrons. Zinc having highest the potential of E naught, because zinc 2 positive in the D10 configuration is very stable. Okay, it don't want to, like, M3 don't want to reduce to M2 positive. Zinc 2 positive in the D10 configuration, because D10 is fully filled, so it's going to be very stable. Manganese have high value because the manganese 2 positive, that is D5, is very stable, so it is going to show high value. It wants to convert to D5. Iron having low value because iron 3 positive is stable already, and because it is in the D5 configuration, half filled subshell. Now vanadium having low value because vanadium in the 2 positive, uh, having D3 configuration and having also T2G stability, which is stable. So it is going to show low E naught value. Now some key points to remember. The first one, oxidation state. One of most notable feature of transition elements, which is a great variety of oxidation state they exhibit in their compounds. So this was the table where we have observed in the first series how the oxidation states are shown by the elements. In the middle or near of the middle, we have seen that maximum number of oxidation state are shown by the elements, and in the extremes, that left and right extremes, the oxidation state number is decreased, shown by the elements. And understanding the E naught values, M3 positive to M2 positive. E naught value indicate the relative ease of reduction of M3 positive ion to M2 positive ion. And we have observed this table where 3D series are given from scandium to zinc, and their E naught values are given M2 positive to M also and M3 positive to M2 positive also. We have seen the manganese, iron, cobalt, right, vanadium, their values, that why they are showing like trend, and what's their explanation. We have seen that. So the lower value means that M3 positive is harder to reduce, and that's why it is going to show the lower value of the E naught. So that's what we have observed according to this table. Okay. So thank you so much. That's all for the today's chemistry session. Thank you.